Forces and role. A static breakdown. We will see it early. Alright, let's start with the basics. Gravity pulls the nozzle straight down. Nozzle, see here. Gravity pulls the nozzle straight down. But when the ship rolls, it's like the force is getting pushed sideways. Is that right? When the ship rolls like this, the force is getting pushed sideways also. Right? Yes, exactly. The force of gravity always acts vertically, but because the ship is rolling, we decompose the force into components that act along the horizontal, that's transverse and vertical axis of ship's frame. So it's like we are reorienting the gravity's direction based on the ship's tilt. Why are we reorienting the gravity's direction? Because the ship is tilting. Is there a specific reason we are choosing sine and cosine to break the components? Is there a specific reason we are choosing sine and cosine to break down the components, to break the components? Yes, it's a geometry. When the ship tilts by an angle of alpha, the vertical component W becomes W cos alpha. This is your W. Here we can see this W weight. This is the W weight. This is the ship frame. This is the angle. This is the rotation. So this alpha becomes vertical component becomes W cos alpha. So this is the vertical component W cos alpha. That's a vertical component. This is the W that goes like this, and the horizontal component becomes W sine alpha. Sine alpha. Alpha is the ship tilt angle. Here the question is that, is there a specific reason why are we choosing sine and cosine to break the components? Yes, it's geometry, because when the ship tilts by an angle alpha, the vertical component becomes W cos alpha, and because that's adjacent to the side angle, and transverse component is W sine alpha, that's opposite. This basic breakdown helps us understand the load distribution in both directions. But there's still more to consider, like the motion of the ship, dynamic forces. What happens when the ship moves? Okay, so gravity divides into components when the ship rolls. That's right. But what happens when the vessel is moving? When the vessel is moving, it has dynamic forces. We are not just dealing with static forces alone, right? When the vessel is moving, what happens when the vessel is moving? We are not just dealing with the static forces alone. Alright, when the ship rolls, it accelerates angularly. So we have to account for the dynamic forces due to the angular acceleration. Hold on. I get that angular acceleration happens when the object's rotational speed changes. Okay, when does that angular acceleration happens? When an object's rotational speed changes, angular acceleration happens. But how do we quantify that force? And why do we even need to care about the angular acceleration in this context? Great questions. We care about the angular acceleration because it creates resisting force that the nacelle experiences. That nacelle resists the changes in its rotational state because of its moment of inertia. We calculate the force using the equation F dynamic m times r times this angular acceleration. Theta double dot is angular acceleration, r is the distance from the roll axis, and m is the mass of the nozzle. But wait, angular acceleration is a change in rotational speed. Is it really about the ship rolling, or are there other factors that affect theta? Is it only the ship rolling about only the alpha angle, or is there other factors that affect the theta double dot? This is the angular acceleration. Other factors also affecting the angular acceleration. What are those? Great points. It's related to the roll period of the ship, how fast it oscillates. For example, if the ship accelerates very fast, then it will have a lot of force. So it depends on The angular acceleration is tied to the roll period of the ship and how fast it accelerates. The angular velocity is tied to the roll period. Angular acceleration is just rate of change of the angular velocity. So angular velocity is related to the roll period, tied to the roll period. Angular acceleration is just rate of change of angular velocity. So if the ship rolls faster, the forces become larger, right? If the ship rolls faster, the forces become larger. Exactly. A shorter roll period, if time period t, shorter roll period means faster acceleration and more dynamic force. If t is less, that means your acceleration will be acceleration theta double naught. It will goes up. If time goes, roll period goes down, angular acceleration goes up. That what does mean? Like a shorter roll period means faster acceleration and more dynamic force. A longer roll period, that means that less force we generate because the nacelle has more time to settle into each position. Inertial and non-inertial frames. What's the difference? I keep hearing about inertial non-inertial reference frames. What does that really mean? Why is it important for us to even care about this in this context? This is crucial. An inertial frame is the one where no external forces are acting on an object. Things move in straight line unless acted upon. Things move in straight line unless acted upon. But when the ship rolls, we are in a non-inertial frame, reference frame, because the ship itself is accelerating. In a non-inertial frame, we experience fixed force, which are not the actual forces but the result from the ship's most acceleration. So these fixed forces are fake forces that appear because we are accelerating with ship. What exactly do we calculate with them? What exactly do we calculate with them? These fixed forces are what we call idle forces. They arise due to angular acceleration of the vessel. They are proportional to the mass and nacelle and the distance from the center of rotation. They are proportional to the mass, distance from the center of rotation, angular acceleration. So the faster the ship rolls, that means shorter the roll period, greater the idle force. That's right. And these forces can significantly impact the stability of the nacelle on the transport frame. Heave and roll interaction. How do these forces mix? Now we are dealing with both roll and heave. So when the ship moves up and down because of waves, when the ship moves up and down because of waves, how does that interact with the roll forces? How does that interact with the roll forces? When the ship heaves means goes up and down. That's a vertical acceleration. But because the ship is tilted, that acceleration is projected into x and z directions. So we have the forces don't just go straight down; they get spread out. They don't go just straight down. They get spread out into the other directions due to the tilt. How do we calculate that? We break the vertical acceleration into components along x and z. So fx heave, f is at heave, w into alpha heave sine alpha, a heave into cos alpha. Wait, does this mean that heave and roll forces can combine in a way that they amplify each other? So if the heave is strong enough and the ship rolls at the same time, the nacelle will experience a huge force in both directions. Yes, if the heave is strong enough and ship rolls at the same time, the nacelle will experience a huge forces in both directions. Exactly, that's why we need to account for both effects. Heave can increase the dynamic loads in both directions, especially when they combine with roll. So total load, how do we account for all of it? So now we got static, dynamic and combined forces from heave and roll. But how do we figure out that total force acting on the nozzle? This combined is nothing but the combined of heave and roll. The force from heave and roll. So we sum up all the forces in x directions, z directions, and we have the total load in each direction of static and dynamic and combined components. So we are combining the effects of roll and heave with the static weight. We are just comparing the effects of roll and heave with the static weight, and then ensuring the system can handle the peak forces. Yes, if we get the load calculation wrong, we risk structural failure. The lasting system, the frame, even the deck structure must be capable of withstanding the maximum possible load. I see now every little detail from the roll period, COG height can dramatically change the forces. This is the R value, this is the T value. So I see now. I see now every little detail, from the roll period to the sewage height, that dramatically change the forces acting on an asset. This is not just math, it's about predicting the real world behavior. That's why we model everything, simulate different scenarios, and always overestimate the forces to ensure safety margin. Engineering is not about perfect answers, it's always about managing the worst case scenarios. And understanding those forces mean we can design the best possible solutions. That's the true goal. Understanding these forces mean we can design the best possible solution. Engineering is about understanding complexity. Even the smallest change in motion can have huge consequences. By asking the right questions, we can ensure the design is always well informed and safe.